All right, try to squeeze some of these in. Locate the absolute extrema of the function on the indicated interval. Okay, so one of the things we've been doing is we've been doing relatives so much that actually when Adriana, you asked me this morning, kind of threw me off a little bit. And absolute extrema means that you can actually have, the things happen on the endpoints. So we just have to test those. So that was escape in my brain. So that means then that we will have to test this one and this one. And then we will have to look for anywhere in between where the derivative is 0. So let's go ahead and figure out what is happening in between. Okay, these guys are easy to plug in. We can get those values. But let's find what's happening in between. And I'm probably going to need another sheet of paper. This one we can actually kind of squeeze here. But for the other ones, I will grab something. I'm talking to myself. F of x is 3 cosine of x. So if I want the derivative to locate any spots where you've got extrema, relative extrema, you'll have to take the derivative and then we will set it equal to 0. But this is the derivative equation. Okay. All right. Well, let's do the negative 3 sine x. Set it equal to 0. Divide by negative 3. We are looking for all the locations where sine is 0 that fall in between here. So we are looking at pi over 2 to 3 pi over 2. So where is sine 0? And you will find that it's right there. So this means that x equals pi. And that's the only location that actually it happens. So this means we would put pi right here in the middle. And then we would have pi over 2 here and 3 pi over 2 there. But really, this is really a chart. I really shouldn't do it like that. Should look more like this. Pi and then pi over 2. 3 pi over 2. Okay. All right. So really, it's like this because we want to find out what they are. If there is a max or a minimum, it would happen here in between and then possibly at these two endpoints. So let's go ahead and plug it in here. So let's start with the pi, since we just figured out that it happens at pi. The cosine of pi is actually -1. -1 times 3 is going to be -3. Go to pi over 2. Pi over 2 is actually 0. When you pi over 2, the cosine of pi over 2 is 0. 0 times 3 is that. And then 3 pi over 2, actually the cosine is 0. So 3 times 0 is also 0. So it looks like we have an absolute minimum at -3. And if we put at x equals pi, -3, that's totally sufficient, totally fine. And then you'll see that these guys are actually tied for that absolute maximum. And if you were to graph this guy, it would have looked something like this. All right, so that both of those top parts of the function are 0, and then this guy would be -3. All right. All right, suppose the second derivative of this equals this function, and the critical values of the function of the first derivative are actually -1, 0, and 1. So use the second derivative test to determine which critical numbers, if any, give a relative maximum. Okay, so somebody has done basically the grunt work for us. All right, so we got the second derivative here. We got critical values. So what we're going to do is we're just going to plug these in, and then we'll determine whether or not it's concave up or concave down at those points. So we've got -1, 0, and then +1. All right, so plugging in a -1, we get to -4 plus 2, that's -2. 0 is going to be 0, and then 1 is going to be 4 minus. It's going to be +2. Okay, so what this means then is that it's negative here, so that would have been concave down, that would be a max. Okay, this is positive, it would be a min. This guy here For as far as relative max and mins, it fails the test, but that means that is where it switches over from concave down to concave up. So if you call this an inflection point, that's right. Okay. So this guy right here, we can say at x equals -1, there's a relative min. At x equals +1, there is a relative max. Now, it's only asking for the relative max, so calling that one a min is actually irrelevant. And then at x equals 0 is an inflection point. There you go. I can't spell inflection. Okay. All right, so number 3, determine whether the mean value theorem can be applied to f on the closed interval a to b. So for a and b, we've got lowercase a, lowercase b, a and b. And if it can be applied, find all the values of c that would satisfy the theorem. If not, explain why not and give the interval where it could be applied. Okay, so let's look at this guy. Now, if you remember, the condition for the mean value theorem is that this guy has to be, there can't be any gaps, okay? It's got to be continuous, okay? And everywhere along that continuous curve, it has to be differentiable except the endpoints. It doesn't matter that there's a sharp point at each one of the endpoints. That doesn't matter, okay? As long as it's differentiable everywhere in between, okay, then, and it's continuous, then you can apply the mean value theorem, all right? This guy right here is good. He is a trig function that looks like he's kind of like, I don't know, maybe it looks something like this. Okay, I don't know. But he is going to be just fine. There's no place where you're going to be dividing by 0. B, on the other hand, there is, okay? So to find the mean value theorem, we want to find the c that would satisfy the theorem, which means that along this interval, we're going to find the average, the average rate of change there. We're going to find that, and then we want to find the c value that equals that. Okay, let's go ahead and do f of 0, and that'd be 0 plus cosine of 0, and that's going to be 1. Okay, so f of 2 pi is 1/2 times 2 pi is pi, and the cosine of 2 pi is 1. So we got that. Okay. So then what you do is you've got to find the slope of the endpoints, right? So what is the slope at the very end? Now, the mean value theorem says that there's somewhere along the way you were at the average rate of change, that same rate. So now we've got the slope, okay, is going to be I'm trying to figure out, let's call it just m, okay, m. And we've got f of 2 pi minus f of 0 over 2 pi minus 0. Okay, that's the slope. That's going to be, we already figured that out, so that's pi plus 1 minus 1, so this guy minus that, over 2 pi. That ends up being pi over 2 pi, and the pi's cancel out, so it looks like we got 1/2. Okay, so this means then 1/2 equals the derivative. Okay, so actually let's do it like this. You know what, I'm actually going to take a sheet of paper here, zoom in a little bit. Okay, so let's do the derivative is 1/2 plus, that's going to be minus sine, negative sine. Okay, now this is the derivative, so this derivative, what we're going to do then is we're going to go ahead and we can call this guy c, because at this point we want to know, this just c is just the common letter that they use, okay, and we want to know where it equals 1/2, okay, oops. All right, so that means then that we're going to add a negative. Okay, and that would give us 0 equals negative sine c. And if I divide it by negative 1, 0, c has to be, the only place where it is 0 is actually pi, from 0 to 2 pi. Sine is 0 at pi, so it looks like c has to be pi. Okay, that's the only place. All right, now this guy, there's an issue. There's an issue at 3. This guy is an asymptote, and it looks like he's, when it's top heavy, this means that this guy will shoot off to positive infinity, right? No, this is going to have slant asymptotes. But we don't need to know that. What we want to know is where the vertical asymptotes are, because those are going to be the places where there is not continuity. So we would say no, MVT does not apply. Okay. The function is discontinuous at x equals 3. Okay. And we could say that it's good to go. Applies on negative infinity to 3, and from 3 to infinity. Okay, and close interval, is that what it says, right? And give an interval where it could be applied. So the mean value theorem, you have to give closed ones, so we might want to say that it doesn't actually equal at 3, but we could kind of like change the number because it doesn't specify, give an interval where it could be applied. So I mean, we could just say from 4 to 5, okay? And I could see this being like a multiple choice question. And then this guy could be from, I don't know, like -6 to -5. Those, and countless others, right? But these are just 2 examples that would show, okay, if we were on this side of this function, we could use MVP, and if we are on this side, anywhere over here is just fine, okay? And we could even develop this sentence a little better and just say, as long as it's not 3, you're good to go. Just as long as you're communicating in that way. All right, so, it's time. Let's stop that right here. Here we go. It's a long video.